This is Science Max, Experiments at Large. Science Max!
Greetings, Science Maximites. Take a moment and imagine with me, if you will, a time when the only way to light your house was with candles or oil lamps. There was no electricity. That meant no power tools, no video games, no telephones, and worst of all, no TV. Fortunately, we live in a world of electricity. If you've ever lost power in your city or neighborhood, you know how hard it is to get by without electricity, even for one day. But where does it all come from? Where do we get this electricity that we use all the time? We make it. That's the cool thing. And I can show you how to make it as well. Check it out. All you need is an electric motor. Electric motors are pretty simple. All you do is get a battery and you attach it to the electric motor, and that makes it work. There we go. Attached to the battery, it spins. But if you spin the electric motor, it creates electricity. And that's what we're gonna look at today, creating electricity. We're gonna build a wind turbine. But first, you need an electric motor. And you can probably get one from a broken toy. Just make sure that the toy is broken and that the broken part isn't the electric motor.
Here's what you need: index cards or construction paper, scissors, push pins, science tape,
It's the same as invisible tape, except I use this one for science.
a cork, chopsticks, craft sticks, and modeling clay. And remember, all the steps for this experiment are on our website. To begin, cut the index cards into strips and tape down a push pin so it sticks out. Then fold over the index card and tape it together. Then stick the pin into the cork and repeat that step.
If you want as many blades as you can get on your fan, you're welcome to do that.
Next, take your modeling clay and stick the chopsticks in, then tape the craft sticks in between with science tape. Then take the motor and stick the cork on the end, then wedge the motor in between the craft sticks and tape it down so it stays put.
And there you go, a fan that will spin in the wind.
You want to adjust the fan blades so they all face on a bit of an angle. That way they will catch the wind and spin.
There we go. Now when it spins, it will create electricity. I'll show you with this. It's a multimeter. And a multimeter measures little amounts of electric current. There. The hairdryer makes wind, spinning the fan blades, and we are creating electricity. Now, pretty much all electricity that you make comes down to turning a generator. A small motor like this isn't gonna produce a lot of electricity, barely enough to power one tiny little LED, but it's a start. And a good start is all we need, because today, on Science Max Experiments at Large, we're gonna look at all kinds of different ways of generating electricity. Plus, I wanna find out just how much electricity one human being can generate. Although, one human being is gonna be kinda lonely, I'm gonna need an expert. Oh, I know, Anthony from the Ontario Science Centre. He can help. I wonder if he's busy. Well, come on. Phil? So I was wondering if you could help me with an experiment. I want to generate as much electricity with human power. What do you think?
I think that sounds awesome.
Okay, great. Let's go back to Science Max headquarters.
Is that the portal?
Yeah. Don't worry, all the kinks are worked out. I know what it is. It's this. Where did you end up?
I was in the vents.
Oh, I ended up in the bathroom. All right, well, now that we're here. Okay, so this is what I started with. And this is just, you know, an electric motor, right?
Right.
So you can generate electricity, you spin it, so I figured in order to generate more electricity, you get a bigger generator?
Exactly, yeah. The bigger the generator, the bigger the magnet, the more the copper, the more the electricity.
Oh, well, you know what we should do is we should just get an even bigger one, like a giant one that they use in like at a power plant or something, or?
Not quite. That would be too big for a person to be able to turn. It'd just be impossible.
So do you think this is a good size?
I think this is a great size.
Okay, so that's good.
This is called a multimeter. We're gonna hook up the wires. I will do black to black.
Black to black.
The red. And as you turn our generator, we can see just how much electricity we're generating. Okay, so
Here, you hold on to that.
This,
and
you
I'll
can
turn
start
the
turning it.
generator.
Now it's time to play How Much Electricity Did They Make?
2.4 volts, yeah, it's not bad.
Oh, 2.4, yeah, it's not great.
That's just enough to power a small LED flashlight. Better keep trying, boys.
I got some handles here that we're going to attach
that
to
would be
the
perfect.
end of the generator so
Yeah.
we can spin it.
Okay, let's try.
No matter how fast I cranked the large handle, I couldn't make any more electricity than before.
Okay, let's try something else.
But it's a smaller handle.
Perfect, okay, yeah.
That's good?
Yeah, well, maybe it'll let us get more spins in.
Oh, yeah, because I don't have to make as big a circle.
Exactly. Yeah, it's working already. We're up to like 3.5,
Now, how much electricity is Phil making?
4.5.
That's the same as 3 AA batteries. Maybe enough to power a toy car. Still, a long way to go.
Yeah, it's a lot higher with the faster spins. Oh, all right. You okay?
I'm okay.
Maybe we could use like some gears or something like that.
Oh, yes, you know, that's a good idea because this circle that I'm making here, I can only go so fast. So
Yeah.
maybe with gears, you can do 1 circle here equals like 10 circles on the other gear.
Exactly.
Yeah.
Okay, so kind of like the gears on like a bike.
Yeah, the gears on a bike or something like that. A bike! Of course! Yeah, so we get a bike and we attach the back tire to the generator.
The generator, and then you can use the pedals of the big gear to power the small gears.
Okay, great. We'll go get a bike.
Yeah.
Yeah, high five. All right. Oh, right, they're over here. This is a generator. It generates electricity when you spin it. But how does it work? What wizardry is inside? Well, actually, generating an electric current is fairly simple. All you need is 2 things. First, you need a conductor, like this coil of copper wire, and you need a magnet. Now, this is a galvanometer. It measures small amounts of electric current, and I have my copper wire attached to it. Watch as I put the magnet inside the copper. I get a little bit of an electric current, and then I take it out, it goes in the other direction. A little bit going this way, and then I take it out, a little bit going that way. Positive, negative, positive, negative. This kind of current that goes back and forth is called alternating current, or AC. It's the same kind of electricity you have in your house. But here's the cool thing. Watch this. I put the magnet in and I leave it. It goes back to 0. You only get electricity when you move the magnet. All right, so let's create our generator. Instead of starting with a copper coil like this, what if we just had the magnet and we have it staying still, like that, and we move the conductor past it, like spinning? It's good, but not great, because we're only getting a little bit of electricity as it passes. So let's make it more efficient. Let's put in some more magnets. 1 on either side, and 1 on the top. And now when we spin it, it goes past all of these magnets, and every time we get a little bit of electric current. Well, this is how a generator works. If you take an electric motor or a generator apart, you can see there's a coil of copper wires on the shaft, and it spins around like this. And on the inside, there are magnets. So there you go. When you put it together and spin it, you get an electric current. Or if you put an electric current in it, it will spin, just like an electric motor. And that is how a generator works.
Anthony and I are trying to create as much electricity as we can using just human power. But so far, it hasn't been going so well. It all comes down to how fast we can spin the generator.
Maybe we could use like some gears or something like that.
In order to get it spinning really fast, we're gonna use a bike. It's just a matter of getting a bike, taking off the wheel, putting it on a stand,
It is now a stationary bike. It'll be even more stationary once we screw it down.
and attaching the generator.
All right, the bike generator, bike-orator. What should we call this thing?
Bike-nator.
Bike-nomator. I like it. So, okay, let's go over what we've got here.
Okay, so we've got 2 gears. We've got a big one, we got a small one. We turn our pedals, and the big gear turns the small one.
So this is the whole point of this build, is so that we can get one revolution here means a whole bunch is spinning there.
Exactly. The more we get here, the more our generator spins and the more electricity we get. We get tons.
Awesome. And obviously using bike, because you're using your legs.
The strongest muscles in your body.
Awesome. Okay, so now what's with this horn? That is a loud horn.
I know. I tried to warn you.
That is great. I love that.
So Anthony and I hop on and give it a pedal. We pedal as hard as we can, and we produce a pretty good amount of electricity. How much electricity did they produce?
We got up to maybe like 18 there. You did a pretty good job.
That's enough for a power tool, like a drill.
It's good. You know what? This works well, I think, for keeping a good number for a long period of time.
Yeah.
So we can get up to like 18, 20, but it doesn't, we can't really get any higher than that.
Yeah, you know what we need is like one really hard pull, like all of a sudden. That way you can get like a spike.
Yeah, you're right. So it's like instead of putting all that effort into it going for a long time, you put all the effort into one quick motion.
Exactly.
Yeah, good idea. So you wrap a rope around here and then you just pull it.
Exactly.
And that'd be a really fast motion. Spin it really quick and get a very high number.
High spike, exactly.
Okay. You know, we're gonna have to take the bike apart though.
Okay,
All right. Well, it's science.
Okay, cool. So I'll just get.
Oh, you know what? We actually don't have to take the whole bike apart. We just have to take the generator off.
Oh, right. Okay.
Okay,
Hang on a sec. I got it.
And maybe we should attach the horn to the next thing too.
What do you know?
Turn it off!
It's so loud.
So you want to generate some electricity. But what do you choose to generate that electricity? Hydro? Nuclear? Coal? Solar? Who knows? I do. I know. And soon, so will you. In order to generate electricity, you need to turn the generator. Turn the generator. One of the most common ways to turn the generator is to use one of these. It's a steam engine. Usually they're a lot bigger. You see, you heat the water to boil it and turn it to steam, which works a piston, which turns the generator. Huh? Pretty amazing, right? But what it really boils down to is heating water to make steam. Boil water to make steam to turn the generator. Coal power. Burn the coal to boil water to make steam to turn the generator. Natural gas. That's different, right? Nope. Burn the gas to boil water to make steam to turn the generator. Nuclear power. That's different, right? Nope. It creates heat, which you use to boil water to make steam to turn the generator. Wind power. We don't even need heat for that. Just use the wind to spin the fan to turn the generator. Hydropower. Just pour water across something that spins to turn the generator. No matter what, making electricity always comes down to turning the generator. It's always yada yada, yada yada, turn the generator. Except for solar. Solar does not work like that. But other than that, it's always yada yada, yada yada to turn the generator. And now you know your electricity generation. Hey, Ramona, you wanna come and give me a hand over here? My arm is getting tired.
Whew, it is hot out here. Oh, in order to generate electricity, you need to spin a generator. Most forms of electricity generation work like that, but not solar. Solar panels like this one generate electricity from the sun's energy. So, how do they do it? Well, this is a solar panel. Okay, it's not really a solar panel, I just sort of put this together, but it works the same way. There are two plates, and on these plates are electrons. I've got golf ball electrons up here, ping pong ball electrons down here, but they're all the same thing. Now, this happy little fellow is a photon, energy from the sun in handy-dandy particle form. What happens is photons come from the sun and hit the top plate and knock some electrons from one side to the other, like this. And that knocks over some electrons. Now, these extra electrons travel up a wire in the form of electricity, and we can use them to do work for us. Then they change to the other charge, go back, and we start the process all over again. That is how solar panels work. But remember, it only works when there's sun and photons.
Anthony and I are trying to generate electricity using human power. Spinning the generator didn't work too well, but we found if we used some gears, like those on a bike, it worked better.
You know what we need is like one really hard pull, like all of a sudden.
Using gears is a great way to get work done. The good news is there are generators with gears already in them. That means if we can turn the spindle once, the gears inside will spin the coil a lot of times. The only downside, turning the spindle gets harder the higher the gear. Anthony and I attach a spindle and then we wind up the rope, which takes a while.
Okay, so the plan is, it's on a big spool now.
Yeah.
And you just run as fast as you can.
Got it.
And we'll hopefully get as many revolutions as we can, depending on how fast your top speed is.
Okay.
Sounds good?
Sounds good. I can be pretty quick.
Okay, good. All right.
Ready?
On your mark.
Uh-huh.
Get set. Go.
How much electricity did they create? 24 volts.
Actually, not bad.
That's enough to power their own personal scooter. Not too shabby, boys.
We need like a hard pull all at once.
Yeah, from something like really big. So what if we could get like really high, like up there? Could we attach the generator up there? You could jump down from there.
And I would hang on the rope?
Yeah.
Yeah, it's good, but I don't want to jump from up there. Oh, what if we put a pulley up there?
That
and
would
then
work.
the rope goes through the pulley and then back down, and then I jump from somewhere much safer, like just on top of here onto a crash mat or something.
That sounds great.
And that's my full body weight on the rope.
That sounds great.
All right, high fives.
Yeah.
Tidal power in 60 seconds.
By now you know that in order to create electricity, you need to spin a generator. Scientists and engineers are always coming up with lots of new ways to use natural forces of the Earth to spin a generator and create electricity. One of those natural forces is the power of the tides. You see, the water in the oceans doesn't stay still. Every few hours, the water, or the tide, goes out. And then a few hours later, it comes back in. So, if you attach a paddle wheel in the water and attach that to a generator, when the tide goes out, it creates electricity. When the tide comes back in, it creates electricity. That is how you create electricity using the power of the tides. It's water power. In fact, hydroelectricity is also using water power. Do we have time to talk about hydroelectric? We don't have time? We don't. Okay, maybe come back.
Hydroelectric power in 20 seconds.
20 seconds? Okay, hydroelectricity comes from water. Hydro means water. So all you have to do is find a place where water pours down from a height. And you can put a generator in there, and ta-da! You're creating electricity with the power of hydro. Ha 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 ha! I did it.
Anthony and I have pulled and pedaled, and now we're going to hang on to the rope and use our whole body weight to spin the generator as fast as possible.
Okay.
Okay.
Crash mat. Let me test it out.
Looks good.
Yep, it's good for crashing. So I go up here. Okay, I go up here.
Climb on up. We'll get you the rope. Got your helmet for safety.
Helmet for safety, crash mat for safety. So we have the rope, and it goes up through that pulley, and then back down to our generator with a spindle on it. And as I fall, the spindle will turn.
Exactly.
And hopefully the speed of me falling and holding and yanking it down as hard as I can will be the biggest spike of electricity yet.
That's right. We'll be measuring it on our multimeter here.
Okay.
Okay.
Ready?
You ready?
Yeah.
Here we go. 3, 2, 1.
I jump down and my whole body weight pulls on the line.
Oh, that was awesome. That was like our biggest spike ever. That was amazing.
All right, high fives. Biggest spike ever. Is it enough to power my house?
Nope.
How much electricity did Phil generate? Almost 30 volts. How much does he need to power his house? 120 volts. he's still off by quite a bit.
Well, we've learned something. Nuclear,
Wind,
hydro,
solar,
natural gas,
coal power.
It's all great ways to generate electricity.
Yeah.
And human power,
Not so much.
not as good. But human power is more fun.
Yeah, way more fun.
Yeah, so your turn?
Yes!
Okay.
Give me,
You
give
take
me.
the helmet and I'll take the multimeter.
Okay.
And then we'll go and we'll do it again. Okay. Wait, I gotta wind it up.
Greetings, Science Maximites, and welcome to... Can you hear me? Greetings, Science Max! You can't... hold on a second. Greetings, Science... Yeah, that's much better. Greetings, Science Maximites, and welcome to Science Max Experiments at Large. Today, we're going to be talking about sound. Sound is all around us. We use it every day, but what is it really? Sound is energy. Let's say that this is the... No, stay. Stay. Okay. That this spring is the sound of my voice. When I make noise, it travels away from me in a wave. One air molecule vibrates the next, air molecule vibrates the next, and it looks like a wave. And when there's a little bit of energy, the wave doesn't move very much. Science. But when there's a lot of energy, the wave moves a lot. Science! What do we do? What do we do to make sound louder? This is the Science Max theme song. But it's not very loud because the speaker on my phone isn't designed to make super loud noises. So what we're going to do is find ways to make the volume of that song as loud as possible. Here is one way. Take a phone playing some music and put it in a glass. Make sure the glass is empty, of course. Huh? And suddenly, it's a lot louder. Wow! Why this works is one of the things we're gonna be looking at today. So that's what we're gonna do today on Science Max Experiments at Large. We're gonna learn how to make sound louder, as loud as we can. But I'm gonna need an expert to help me. Oh, I know, Michaela from the Ontario Science Centre. She's very smart. All I need to do is go to the Ontario Science Centre and see if she's busy.
Are you okay?
Yeah, Michaela, it's good to see you.
Nice to see you too.
That was weird. I was wondering if you could give me a hand with an experiment.
Oh, I'd love to, yeah.
It's a sound experiment.
Sounds awesome.
Right on. Okay, we'll take the portal. We'll go back to Science Max headquarters.
Oh, we take the portal? Cool.
Haven't you taken the portal before?
No, don't you remember it wasn't working last time?
Oh, well, it's
Is it working?
fixed this time. Yeah, no, it'll be great. Trust me. Here we go.
Whoa. What's going on, Phil? Is everything okay?
Usually when I come through the portal, I land on something or something falls on me or...
Not today. It's your lucky day.
I guess so.
Safe landing.
Safe landing.
Nice.
High five. All right, so let's get started.
Okay, cool.
This is the experiment I want to max out today, Michaela. I know. Pretty impressive, right? No, hold on.
Okay.
So I take my phone and I play some music on my phone and it's louder, right?
Check it out. Phil, you've just made yourself a resonance chamber.
A resonance chamber.
A
Very
resonance
nice.
chamber is what we say when we're trying to describe how the sound is amplified. So if the sound's coming in from one direction, it's bouncing around, not really losing energy. So when more sound comes in, that's amplified. We hear it a lot louder.
That's cool. So that's what I want to do. Hold on, let me turn this up. That's what I want to do today. I want to max out as much sound as we can get out of the Science Max theme song, which
I'm
is
so excited.
totally awesome. So what else can we do to do that?
Well, there's a couple avenues I'm thinking. Do you want to try something with electricity or without electricity?
That's because with electricity, we're talking speaker systems and
Yeah.
Right. So
We
why
can
don't we
get into
do no electricity for now, and then we
Alright.
can jump to electricity when we feel we've exhausted everything that's non-electric.
Cool. So I was thinking we could try to make a megaphone, because if we have a lot of sound, we could, funnel it in one direction, and then it would be louder.
Okay.
What do
Yeah.
you
So
think?
the megaphone's pretty easy to make, right? We could just use, in fact, we could use this piece of paper, right?
Yeah, let's try it. What do you think?
I think it's very megaphony. Science taping it up.
Okay, ready? Okay, turn it on. Play it. And doesn't sound, but what if I do this?
Hey, there it is. I know.
Oh,
That song.
yeah? You hear it?
Yeah. Oh, I hear it.
Okay. So that worked pretty well. So.
Oh, yeah, it works. Works well.
So, okay, so this is pretty easy, right?
Yeah.
Megaphone?
Oh, yeah.
So why don't we max this out? Why don't we make a giant megaphone and see if it makes a big difference?
I think it will. Let's do it.
Sounds good. Let's get started. All sound is vibration, but it's really hard to learn about that vibration if you can't see it. I mean, sound is invisible, right? Well, here's a way that you can make sound visible. All you need is some plastic wrap and salt and a bowl, just a regular bowl, and an elastic, like this. So what you do is you take the plastic wrap and cut off a piece just large enough to fit over the bowl, and then use the elastic to wrap around the bowl to keep the plastic tight. Pour some salt on the bowl, and then watch this. Hello, vibrating salt.
The plastic wrap is stretched tight over the bowl, making it like a drum. A drum that's very sensitive to sound vibrations. Your ear works the same way. That's why we call it an ear drum. The vibrations from my voice make the plastic wrap vibrate, and that makes the salt dance.
But there's more. Let's max this out. This is a Chladni plate, and what it is just a piece of metal on a platform that vibrates up and down to a frequency which I can program with this dial here. And when the sound waves vibrate the plate, they can interact in ways that make the sand form interesting patterns. Take a look.
The sounds I'm generating vibrate the plate, make it move like a wave. But when the vibrations reach the edge of the plate, they bounce back and interact with the other waves going the other way. The way these waves interact at different notes is what causes the sand to make these different shapes.
So this is great, but you know what? We can max it out even more. Maxing it out even more. Okay, that's about as much as I can take of that. Whoa.
So Michaela and I are on a quest to make the loudest sound we can. The first step is to make things louder without using electricity. We've looked at a resonance chamber, and now we're going to make a large megaphone. Sounds can be amplified by bouncing sound waves around in a space. When I put my phone into the glass acts as a resonance chamber. The sound waves bounce around inside the glass, and they combine and stack on top of each other. This makes the sound louder. Resonance chambers are used by musical instruments like an acoustic guitar. The wooden chamber bounces the sound waves around, and the sound waves build on each other to make the sound louder. A megaphone bounces sound waves as well. Instead of going off in all directions, a megaphone makes the sound waves all go in one direction. That's one of the reasons why a megaphone makes sounds louder, but only when it's pointed at you. So will a bigger megaphone work better?
So we've made a larger megaphone, which is exactly the same thing. You just take a sheet and you roll it up, except our sheet was plexiglass covered in paper, and we've taped it together so it stays. And the idea here...
Oh yeah, bigger megaphone. We're gonna vibrate even more of the air inside of here, and hopefully this thing will be louder.
Okay, so you're ready to try it with the phone?
Yeah.
I think first we should try it with our voices, though.
Okay.
Now, what's your favorite season?
Awesome, I can totally hear you. That's amazing. And it would be fall. No, summer. Spring?
Think
it's
about it.
anything but winter.
So the maxed out megaphone worked, but we still had to try it with my phone.
Okay.
All right.
Yeah?
Oh yeah. Oh, definitely.
How about now?
No, not so much. Not so much. Oh yeah. No, no.
So that is a
That was
great
cool.
example of non-electrical amplification.
That's right.
Amplified the sounds, no electricity. Okay, bye-bye. All right.
on! Make some noise! Well, how do you make noise? Well, to know that, you gotta know your sound. All sound is vibration. Here, take a closer look. You see? You got... Okay, let's try this again. All sound is vibration. The string of this guitar vibrates, which vibrates the air around it, causing the sound that you hear. Your vocal cords vibrate in your throat, causing you to make a sound. Ah, 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 la, 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 la. Look at this thing. Look at this thing. See how it's shaking back and forth? It's vibrating. Things that make a high sound, they vibrate faster. Vibrating really fast. Things that make a low sound vibrate slowly. High note, vibrating fast. Fast! Fast vibrating! And now you know your sound.
Everything has a resonance, a note that it vibrates best at. Let's say this fish tank is, well, any container where sound would be vibrating, and the waves of water are actually waves of sound. Now, normally, sound waves will bounce around inside the container, off the walls, and go back and forth like that. And how fast I move this piece of wood is the frequency, or the note, that we're playing. I could vibrate this wood very fast and make a high note. I could move this plank very slow and make a low note. And the waves just bounce around inside the container. But there's a speed I can move this plank where the waves stop going side to side and suddenly get twice as big.
The waves bouncing off the sides of the tank are meeting the waves going in the other direction. But what we end up seeing is peaks of the waves not moving side to side, just going up and down, like you see here.
This is the resonant frequency of this container. So, let's max this out. Say I have a wine glass, and I wet my finger, and I rub it around the rim. It vibrates at a certain note. That note is the resonant frequency of this wine glass. So what would happen if we were to play that note back to this wine glass really, really loud?
And yes, this is something you should not try at home.
This note makes the glass vibrate the most.
Finding the perfect note things vibrate best at is great for musical instruments, but it's not great for this wine glass. The sound waves are causing the glass to vibrate a lot. And because this glass is delicate, it can only vibrate so much before it breaks.
The vibrations were so strong that the glass literally shook itself to pieces.
Science! Sorry. Science! Oh, wait.
Science!
Michaela and I have tried a resonance chamber and a giant megaphone to make sound louder. Now it's time to move on to the next step of the plan, using electricity to help us amplify sound. And that means speakers!
So, speakers that you have at home, 3 different speakers here, right?
Looks
3 different
really busy.
cones.
Yeah, there's a lot going on.
So, what's the deal?
Well, here at the bottom, we have a subwoofer.
A subwoofer.
Subwoofer.
So it's a woofer, the word is woofer?
Yep.
And it's, okay, so it's for dogs, right?
No, a subwoofer is for low notes. notes here in our speaker.
Ah.
At the top here, we have a tweeter.
So it's for birds. It's birds, dogs. So low, let me guess, low notes?
Yeah.
Tweeters, high notes?
Yeah, high notes. And then we have this guy here in the middle, and that's called your mid-range speaker.
Oh, that's not nearly a cool name. Now we have speakers, we've taken a look at that, but why don't we take one apart,
Cool.
right?
Yeah,
Because
let's do it.
I've got this one here that I spilled juice on, so it doesn't work anymore. So I've kind of taken it apart. So
Cool.
it's got,
Oh, man, that's awesome.
okay, so it's got the cover. That's cool. So what I find interesting is there's the speaker and the wires, right? Because it's electrical amplification. But check this out. This is just a ring to hold that on. And the rest is just an empty box.
We know what that is. Resonance chamber.
That's right. So that's why it's an empty box. So
Let's take this apart too, see what's going on.
So that's the paper cone, right? So that's that's the drum, I guess. It's like the eardrum, the thing that vibrates.
Yes, yeah, this cool thing vibrates.
So this whole thing.
That's for electromagnet. When we turn this on, the electromagnet goes on and off, and it's causing this whole thing to vibrate.
So that's how it works. It's the electricity turning the electromagnet on and off.
Exactly.
And it's on and off and on and off and on and off and on and off. And then it makes it vibrate at certain speeds, right? Hertz. The number of times it vibrates per second is hertz. What we could do is we could max it out with the speaker and plug the phone into speaker. But this step does not feel like Science Max to me because anybody can do that, right?
Yeah.
You can just turn up your television right now, and that's pretty much the same kind of thing. We need electrical amplification, but maxed out.
Max it up. What are you thinking?
Okay, so I've got a friend, and he's got a stereo system that he built, he put together, and what he does is he tours different cities. So he said he'd bring it by Science Max headquarters.
He's gonna bring it here?
We gotta go outside.
See this thing.
And it's very loud, so we have to go outside.
When's he coming?
Right now. All right, let's go check it out.
Seeing sound vibrations is fun. This kind of speaker is a special kind. It's called a subwoofer, which is designed to give you the low notes, the big rumbly bass sounds. I tilt the speaker so it's facing up and cover it with big sheets of plastic wrap, which I push into the cone. Then, tape it so it's nice and secure. Then, what you need is some cornstarch mud, which is 2 parts cornstarch, 1 part water. I've got some yellow cornstarch and some blue cornstarch. This experiment works the best with low notes. I'm playing a tone through the stereo that is very low. Here's what happens when I turn up the volume.
It's alive! You see, cornstarch mud is a shear thickening fluid, which means when you impact it, it turns solid. So the vibrations from the speaker cone are making the cornstarch mud impact, and that's turning it into a solid. But then it sort of also melts back into a liquid, so you get little columns of cornstarch coming up and falling down again. It's like it's dancing. Whoa! Visual sound waves. Science!
So Michaela and I are going to max out sound. To do that, we need a maxed out sound system. This is gonna be amazing. This
So
is gonna be super maxed out sound experiment. This is
so
James,
pumped.
Michaela.
Hey, James, how are you?
Thanks for coming, buddy. Nice to meet you. So, tell us about your speaker system. It looks a lot like a vehicle.
This is my audio van. It's got 4 15-inch subwoofers in the back. It's got a whole bunch of power to power it, and I'm glad to be here to let you guys hear it today.
Wow.
So if I have a speaker at home, like a little speaker like this, how many watts do you think that would be?
Somewhere between 15 and 25.
15 and 25 watts.
Yes.
And you've got 4,000.
Yes.
So that's a lot more.
Yeah, quite a bit.
And subwoofers, they play low notes.
Yes.
So is that better when you have a van like this?
With a car audio van like this, you want to play low notes. Like your house stereos and that will play anything from 120 to 200 hertz. I'm playing 20 hertz to about 35 max for you guys today.
So that's like a sort of rumble of
Yes,
thunder,
very
kind
low.
of blah, 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 blah,
Yeah.
where you really feel it.
Yes.
Like a train going past almost.
Oh, that's cool.
So we get our hearing protection on and we try it out. I know what you're thinking. Phil, what's the point of having loud music if you can't really hear it? Because we've gone from listening to music to feeling it. The sound waves are so strong that they have become a physical presence. Michaela's hair flies around because the air from the speakers is creating shock waves. The sound waves are so powerful, they move the air back and forth, which makes Michaela's hair dance all over the place. And my hair, not so much.
I'm totally jealous of your long hair.
Yeah, you need to get longer hair.
Okay, hold on. I'll go right.
Okay.
Whoa! Science Max, experiments at large, super sound! High fives.
Yeah,
Okay, ready to go again?
So cool. Yeah, let's do it.
Okay, here we go.
Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're going to be looking at light. Okay. Stay. That wasn't supposed to happen. I was supposed to press that button, and there was supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not going to be doing one experiment. We're going to be doing a number of small experiments because we are going to do a light manipulation challenge. I'm going to get an expert, and she's going to challenge me to a game of light manipulation because I am the master of light. Oh, well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, back to. I'm gonna work on that later. I'm gonna need an expert to help me, though. Oh, I know. Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh, well.
You okay?
Hi.
Hi,
Anne.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now, you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now, you're gonna challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
a little more difficult than the last.
Well, this is gonna be great, because I am the light manipulation master.
Okay, well, we'll see about that.
Okay.
Challenge number 1.
Take a seat.
Oh, well, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm gonna challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right? So, wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew! Doesn't seem to make it any easier to read. Yeah, I got nothing.
Do you give up already?
No, of course I don't give up.
I told you these were gonna be challenging.
This is nothing. I will figure this out. I don't know yet.
You're gonna have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking, not looking. I'm gonna go this way.
I'm gonna wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation.
A lens works by changing the direction of light, too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change. What was only this big before becomes this big when you see it. Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution.
Check it out. It's a giant magnifying lens, and I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right.
I set the lens in front of the ball, which Anne has turned so I can't see what's on it. I add a light.
Shine it on the ball so that it's a little bit better illuminated.
And then sit in the chair and ask Anne to move it so it's aligned.
All right, so bring it to your left. Yeah, keep going, keep going. Keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Try bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy. Solved.
Wait.
What?
That was just the warm-up.
Oh, yeah?
Yep. You ready for challenge number 2?
Challenge number 2!
I've got another ball.
Okay.
With something else written on it.
Wait. Are you coming back?
Nope.
Huh. But I can't even see you from here. Like how am I? Huh.
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right. I'll think of something. So you remember the tennis balls in the wall, right? Right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now, right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror, and the photons would reflect off the mirror and it comes straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope. Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface. And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website.
Step 1, cut the tops off your milk cartons. Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then, get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your two mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go, your very own periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute, the bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see, It lights up. And because infrared light works the same way as visible light, in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror, and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like. The light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television. Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, right. Turn off the television when you leave the room. I solved Anne's first light challenge, seeing something far away, with a lens. It says 71! But now she's moved the ball around a corner, and now I have the solution. Mirror! A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay. Go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens. So we'll use a mirror and the lens to, good. Yeah, okay. I'm gonna sit in the chair. You're in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this. All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I
Nicely
am
done.
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally. Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
But it's dark. Okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. It's being internally reflected, and the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection. Who cares? Well, I can tell you why you should care in 2 words. Fiber optic wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science.
Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Anne? Anne?
Careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do...
No. Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back.
Okay.
I'll be back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What? Look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays, huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is it staying up? So everything outside of the visible spectrum is invisible, right? Wrong! Ha-ha! Bam! Huh?
That is an X-ray, a picture we can take using this part of the spectrum.
We can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. Okay, you got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared.
For those of you keeping score, that's this part of the spectrum right here.
pretty neat, right? I would sell you these, but they're already spoken for. Oh, and here he comes now. Hey, Sal. Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Phil? Is that you?
Yeah,
Do you need the flashlight?
I don't. Turn it off. I can totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here.
Oh.
Right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it.
Okay, here we go.
Oh wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time, it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. We're gonna be making one of the easiest and one of the hardest experiments to do. Here's what we're gonna make, a hot air balloon. And it's pretty easy to make, that's why it's one of the easiest experiments. All you need is a plastic bag, but not any plastic bag. The kind of plastic bags you get at the grocery store to put your fruit in. That kind of plastic is very thin, very light, good for hot air balloons. And you just want to put 2 paper clips on the bottom of the bag to hold the bottom down. Now here's the other thing you need. You need an adult and a hairdryer. Turn the hairdryer on.
Put the heat on the highest setting and the fan on the lowest setting.
The air inside the bag is getting hotter, which means the molecules are moving faster and they're getting further apart, which means there's going to be less of them in the same space. Less molecules means less weight, and that means it's going to be lighter. The bigger the difference in temperature between the air inside the bag and the air outside the bag, the better it's going to work. So I recommend doing this outside, actually, on a cold day. When it's been long enough, turn the hairdryer off and it will float. Haha! Now it won't float very long because the air inside the bag will quickly return to its original temperature and it will no longer be any lighter than the air outside the bag. But it's definitely fun to fly for a while it lasts. So that's what we're gonna do today on Science Max Experiments at Large. We're gonna max out the hot air balloon and make a giant hot air balloon. Yeah, I know what you're thinking. You're thinking, Phil, they already exist. Why don't you just get a giant hot air balloon? I mean, they're big and you... No. There's no fun in that. I want to make one I built myself. I don't think I'm going to be able to fly in it, but it'll still be pretty cool, I bet. I just need someone to help me. Oh, I know. Michaela from the Ontario Science Centre. Hopefully she's not busy. Hey, Michaela, how are you?
Good, how are you?
Good. I was wondering if I could get your help with an experiment. Do you have some time?
Yeah, I'd love to help out.
Awesome.
Sure.
Okay, let's go back to Science Max headquarters and I'll show you what we're gonna do. Okay,
Nice.
so ready? Here we go.
Oh, no, still here. Still here.
Why are we still here? That's weird. Okay, well, I know. No? Why is the code not working?
I think it's the Science Center code. Try the
Oh, it's the lab code. Right.
Phil, are you okay?
Yeah.
Are you okay?
Yeah, no, I'm fine. So, Michaela, I'm glad you're here because today I want to max this out. This is my hot air balloon. It was better before, I smushed it in my pocket, but
what I did is I used a hairdryer, and then I put it in and I heated the air, and then it rises up. So in order to max it out, pretty simple. I just get larger bags, right? And then I thought we could cut them and tape them together to make a much larger balloon.
It's a good idea, but you know, if we're making a hot air balloon, we need to make sure our materials are really light. The duct tape seems a little heavy. Even this bag seems a little heavy to me.
In terms of, oh, you mean the
weight.
kind of plastic it is?
Yeah,
might be a little bit.
it seems really thick, this one.
Well, do you know for sure?
I've never tried it before.
All right, well, that's science. We should try it and see what happens.
Let's try it.
Okay, so I'll cut along the side of the bag. You see that? Carbon dioxide gas. Our bodies breathe in oxygen and breathe out carbon dioxide. Did you see it? Oh, take another look. How about now? No, you didn't see it, right? Because carbon dioxide is invisible unless you freeze it. This is dry ice, frozen carbon dioxide. And this is wet ice. It's not really called wet ice. It's frozen water. Now, you know what temperature water freezes at? Starts with a 0, ends with a, well, it's actually 0 degrees Celsius. And this freezes at -79 degrees Celsius. It's much colder. I have to hold onto it with a glove because if I held onto it with my bare hands, I get frostbite. So here's the experiment. If I pour some liquid water on the dry ice, will it freeze again? Let's find out. Because the dry ice is so much colder than the freezing point of the water begins to freeze from the bottom up in room temperature air right before our eyes. Whoa! Totally frozen! Cool! Cool. In order to build our hot air balloon, Michaela and I are taking clear garbage bags, cutting them along the seams so they end up as one thin sheet of plastic, and taping them all together with duct tape into a balloon. Okay, so that's,
Nice.
how many bags is that?
It's like 12 bags.
Well, so you think that's big enough?
I think so. It's pretty big.
Okay, I think we can stop there. Okay, so where's the opening again?
I think it's on your side.
I hope you didn't duct tape it close. Okay, no, we're good. We're good. So it's going to inflate like this. Wait a minute. Let's make sure it works. Is it working?
Kind of.
I don't know if it's inflating. Okay, good. So it does inflate. It does hold air.
Yeah.
Right? So should we try it?
Yeah, let's try it.
Okay, so we're gonna use a hairdryer. Right? And now we wait. It's working.
Kind
right?
of.
Oh, yeah.
Woohoo.
Okay, it's almost inflated.
All right.
Okay, what do you think?
Yeah, let's try it.
Okay, on the count of 3, we'll throw it, okay?
Okay.
All right. 1, 2, 3. It didn't quite.
Not quite.
Doesn't quite float, huh?
It's still so heavy, Phil. I think we got a couple problems here. The duct tape is really heavy.
Yep.
Also, these bags themselves are really heavy.
Okay, well, if we want to fix the duct tape problem, we could use lighter tape. Like, what if, we use invisible tape, or as I like to call it, science tape.
Science tape.
Which would be lighter than duct tape.
That's a good plan.
But what do we do about the bags?
Have you ever seen those, you know, those dry cleaning bags?
Oh, wait, I've got one. I've got one here.
Cool. Perfect.
Aha!
Yeah, perfect.
Because, you know, when I get my lab coats dry cleaned, so let me see here. Oh yeah, this is much lighter. This is kind of the same material as the grocery store fruit bags, right?
I have a better feeling about this one.
So lighter tape, lighter bag means a much lighter balloon. Okay, well, let's try it. First, I should probably take my lab coat out. This is water. Now, it's ice water. Science! Okay, no, that's not the science part. Here's something you can do at home.
get some ice water and a way to time yourself and stick your hand in the ice water. It's a little hard to stick your hand in ice water for a long period of time because after a while, it starts to hurt. But don't worry, the pain that you're feeling isn't actually because you're damaging anything. It's just your body's way to tell you that you need to take your hand out of the cold water. Yeah, you usually can't do it for very long. But some animals, like seals and whales, they live in ice water all the time. They live in the Arctic, so how do they do it? One word, blubber. Blubber is a layer of fat that protects you from the cold, or protects the seal and a whale. We don't have blubber, but we are today gonna have some blubber because we're gonna make a blubber glove. Blubber glove, I love saying that. Here's how we do it. First, we want blubber. Okay, this isn't blubber, this is lard, which is actually animal fat. You can use lard, you can use margarine or butter or shortening, anything with a lot of fat in it. And remember, this is messy, so definitely get an adult to help you. So we've got our lard, and we need a bag. So what you're gonna do is you're gonna take a scoopful of lard, like this, and you're gonna put it in the bag, like so. Like that. There we go. And then you're gonna start smoothing out the blubber or the lard like this. Because what you wanna do is have a nice thin layer all the way around. See? Starting to work? Yeah. Then seal the bag and tape the edges. A square of blubber. Then do it again. Here, I have 2 bags of blubber, and I've taped all the way around the outside. So I have, a blubber glove. Check it out. So, let's try it out. I stick the blubber glove in the ice water. It's completely working. It is not even cold. The blubber is completely protecting my hand from the ice water. I'm not even remotely cold at all. That is very fun. So, try it yourself. A blubber glove. Now, how do we max out a blubber glove? Watch. Water, ice water. I know for a fact that I wouldn't last more than 10 seconds in here without my blubber suit. I'm gonna make an entire outfit of blubber. I've got them in large plastic bags, and I'm going to get completely suited up in blubber with the help of Trevor and Stephanie. Okay, guys, suit me up. It's very heavy. Let's just go like this. Oh, okay. Time to cut back on the cookies. All right, let's do it. All right. Blubber suit, go! I can't. Okay. Oh, here we go. Good. Okay, so far. Oh. The legs are warm. And oh. Blubber suit! Ha ha ha! I am in seals! Actually, here I am in the ice, and I don't feel too bad. Blubber suit works! Ah, blubber suit's refreshing, actually. You just sit back and chill out. Well, there you go. Blubber suit success. Seals and whales are able to stay in ice water for their whole lives because they have protective layers of blubber, just like I do. Okay, so now all I have to do is get out. Blubber suit! Oh no! My blubber is leaking! I've sprung a leak! My blubber! Oh, my precious blubber! No! What a world! Oh, hey, how you doing? Shut the door, it's cold out there. Cold enough for you, huh? Well, that's nothing. Let me tell you. You know what temperature water freezes at? Yeah, 0 degrees Celsius. But even that is nothing. Let's say it's winter in Winnipeg. It could get down to -20, maybe even -40. But even that's nothing.
liquid nitrogen, minus 196 degrees Celsius. But even that's nothing. The vacuum of space, minus 271 degrees Celsius. But even that's nothing. So, what's the coldest temperature? What's the coldest temperature you can have? It's called absolute zero, minus 273.15 degrees Celsius. At that temperature, all the little wiggling that particles do comes to a stop. Everything is frozen. No more movement, no more energy. Everything stops. It doesn't get any colder than that. Absolute zero is the ultimate nothing. Brr, time to get your mittens on.
Our first hot air balloon didn't float very well.
It's still too heavy, Phil. I think we got a couple problems here.
So we're making a lighter version out of dry cleaning bags and science tape, both lighter materials than our last version. We also went for more of a square shape than our last version, which kind of looked like a sock. Once we were done assembling, we got the hairdryer and tried it again.
Ooh, it's sort of working.
Kinda.
It's inflating. That's something.
It's a start.
It feels warm, like the hairdryer is actually making a lot of warm air in there.
Yeah.
This is definitely working better than the last version because it's so much lighter.
Yeah.
Wait a minute. Almost got it.
Oh,
Yeah, it's sort of working, right?
cool. Kind of.
Okay. Ready?
Are we testing it?
Turning off the hairdryer. Huh. It kind of collapses the moment we turn off the hairdryer,
Not what we expected, was it?
Yeah.
No.
I mean, it sort of works.
The thing is, our balloon is so big that we need to heat up all of the air that's in there. I don't know if this hairdryer is strong enough.
I think you might be right. So we just need something else that pushes heat.
Yeah, more heat.
So
More
like
power.
a heater of some sort. You know, we've got some heaters up in this room actually, and maybe I could just tear one out. We can use that.
I like it.
Okay.
Let's do it. All right.
There.
Got it.
An industrial heater. And this is going to work just the same as our hairdryer. It's going to blow a lot of hot air up here, but this is way more effective than a hairdryer, right?
Yeah, way more powerful.
So we put the balloon over here, hot air comes up, the balloon inflates, and hopefully flies.
Hopefully.
All right, let's get the balloon.
So we put the balloon on the heater and turned it on. But
Doesn't seem like much is happening.
that's because the heater pushes less air, but the air is much hotter, which means it took longer,
Should we have brought a book?
but soon it was inflating.
Definitely a better result than the hairdryer.
Okay, you ready? I think it's gonna work.
It's gonna be awesome.
All right,
Yep.
1, 2, 3, let go.
Lift off.
Yeah, it's like a giant jellyfish.
That's huge.
Uh-oh, it's tilting, No, no! Oh no, it's going back down. Okay, so the balloon flies, which is great.
Awesome.
The problem is it turns over in the air.
Yeah, I noticed that.
And if it turns upside down, then all the hot air comes out and it doesn't fly anymore.
I was thinking next time if we make it bigger, what if we had a little weight at the bottom just to keep it stable?
Oh yeah, okay, I've seen balloons that have sort of an X, like a very light wood that goes across the opening at the bottom.
Oh, cool.
Maybe we could tie a piece of rope to that to keep it weighted. And if the bottom is heavier, then it won't flip over upside down, right?
Love that idea.
So we're gonna weight it at the bottom with a little X so that it doesn't flip over. And we're gonna make a bigger balloon.
We're gonna need more bags.
Oh, right, back to the bag store.
Thanks, sir.
Okay.
Wait for me.
Being a chef is my absolute passion, and cooking up science recipes is my specialty. I'm Buster Beaker, and this is Cooking with Science.
Strange. This spoon is no sharper than it was before. Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker, and today we're cooking with coal. Today we're going to learn how to make a drink cool. Look at this bottle of lemonade. It's warm right now and not very refreshing. So what's the best way to cool this down? We put it in ice, right? But did you know there's an even better recipe than ice? You can make ice colder. It's true. All you need to do is add salt. I've got a second bowl of ice and a second jug of lemonade, and I've got 2 digital thermometers. What I'm going to do is add salt to this bowl. What the salt does is starts to melt the ice, and that actually consumes heat. This is called an endothermic reaction, and it absorbs heat, which makes the ice colder. And as you can see, this bowl of ice still sitting at around 0 degrees Celsius, but this bowl, -8 and falling. Wow. So there you have it, making something even colder than ice would normally make it. That is a way to make a refreshing glass of lemonade. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
With our new heater and lighter materials, our hot air balloon was floating free. That is, until it tipped over. When that happens, all the hot air inside escapes. But Michaela and I have a solution. So we decided to build an even bigger hot air balloon and add a way to keep it upright.
So the process, aside from that, is pretty much the same. We put the end over top of our industrial heater, and I will plug it in.
Get that hair dryer again for good measure.
It's working, it's inflating, but we gotta keep fluffing it up, otherwise it just sort of sags. But you can see the top of the balloon is definitely working. It's a lot bigger than the last one, though. Do you think we made it too big, Michaela?
It's really big. I think it's working.
It's definitely working. Uh-oh, pull your side.
Oh,
Oh, it's totally working. I'm so surprised that this works so well. So the stick is gonna keep it balanced so the bottom faces down, but Michaela's gonna tie a string to the stick so that when it goes up, we can keep it centered. Okay, this looks good. You wanna let it go?
Yeah, are we ready?
Okay.
Okay, 3, 2, 1.
Whoa!
Yeah! So let's recap. The hotter air inside the balloon is less dense than the colder air on the outside. And because we were able to get the air hot enough and the balloon light enough, it floats.
Science Max, experiments at large.
Hot air balloon.
Thank you, Michaela.
Awesome.
That was
so cool.
Wait a minute, who has the string?
Oh, no.
Oh no, oh no, oh no! Oh, hello, Science Maximites. We've got a lot of work today, so I was just getting prepared. You know, taking something flimsy and making it strong, that's what scientists and engineers do every day. And it's also pretty fun. You take something that's not that strong, and by the way you build it or put it together or change its shape, it suddenly becomes a lot stronger than you think it was. So I thought that's what we should do today on Science Max Experiments at Large. We should build something. So we're gonna build an arched bridge, and we're gonna build it out of sugar cubes. So here's what you need. You need some sugar cubes, you need some sandpaper, and you need some modeling clay. So first, you want to make some abutments out of your modeling clay. What is an abutment, you ask? It is this. They distribute the force laterally from one side or the other. I like to use this. This is half a roll of duct tape. And so it fits in just like that, and you see, it's a perfect arch. If you just take sugar cubes and you try to stack them into an arch, it's not going to work because the sugar cubes may not even fit all together, and you can see only the bottoms are touching. I take up the guide and it all falls apart. So here's what you do. You take your sandpaper and you change the squares into trapezoids, and you start sanding down your sugar cubes into trapezoids. Basically, you want one small side and one long side. Thin at the top, wide at the bottom, or wide at the top, thin at the bottom. It's a trapezoid no matter which way you hold it. Put it on the bridge and see. And as you go, you will see if you're doing it right, there will be no gaps. If you go to the Science Max website, there will be a guide that you can use to help you make the sugar cube bridge. so you don't have to spend as long as I did making this one. And then the most important part is the keystone. That's the one that fits in right at the top, just like that. And when it does, you can take away the guide, and it stays up. Isn't that cool? It stays up without any glue, without any mortar, all based on the shape of these sugar cubes. The cool thing is, it'll hold the weight of a whole car, provided you have a very, very small car. The reason why it works is because the weight is distributed along the arch into the abutments and down into the ground. That's what makes an arched bridge so strong. And that's what we're gonna do today. We're gonna max out an arched bridge. So I think I'm gonna need some help though. Maybe Sonia from the Ontario Science Center. She really knows her stuff. Yeah, I'll go there and I'll see if she's busy. All right, come on, let's go. Hey, Sonia.
Hi, Phil. How's it going?
It's going good. I was wondering if you could give me a hand with something.
Okay. What's up?
I'm building, well, it's easier if I show you.
All right.
Do you mind coming back to Science Max headquarters? We can take the portal.
But that thing doesn't always work.
Oh, it is fine. Well, I mean, that worked just fine. Uh-oh, it usually makes a beeping when I do. Oh, it's out of batteries. Oh, I told myself, Phil, charge the remote before you leave the lab, and then I.
Where have you been? Breathe.
The remote ran out of batteries, so I had to run the last 3 kilometers.
It's all right.
Because
You made it.
Long story. So the Sugar Cube Bridge, you had a chance to look at it, right? This works on any scale, right? It should, no matter what size arch, it should be the same, right?
Definitely.
Good, because what I want to do is use these abutments, but go to these abutments.
Oh.
So I'm going to start the bridge here, and I've already created a thing that we can use to put the sugar cubes on as we go up, so that we can make sure that it becomes a perfect arch. Yeah.
Do we have enough sugar for this?
Yep. I got tons of sugar.
Wow.
Yeah. So I think we're gonna need some glue because it's gonna be really hard to get these to stay.
Yep.
To stay right there without a little bit of glue. We're gonna make a giant arch, maybe some walls, and we'll see what happens.
Let's do it.
Oops. An egg. Now you might think of eggs as kind of flimsy, and they do break pretty easily, but eggs are actually stronger than you think. It's because they're, well, egg-shaped. You see, the top of the egg is like a little bit of an arch, and the bottom of the egg is also like an arch. And arches distribute the weight, just like they do in a bridge. Here's how you can experiment with how strong eggs are. First, you want to get a pair of gloves to protect your hands from the shell, just in case anything goes wrong. You should also tell an adult that you're doing this experiment because if it does go wrong, you're gonna have some mess to explain. And also, you should probably put on some safety glasses. Now, here's what you do. Take your egg and carefully put it in your palm just like that. And put it against your other palm, and you're gonna push in directly on either side of the egg. Start pushing harder and harder. You can even lace your fingers and press even harder. And if you do it right, the egg won't break. Pretty amazing, right? So, just how much weight does an egg hold? Can one egg support my entire weight? Let's find out. I'm gonna lift my weight up like this and lower myself down. And no, cannot hold my weight. Can my weight be supported by 2 eggs? Oh, nope. Phil's weight, 4 eggs. Oh, I thought they were gonna do it. Nope. My weight on 8 eggs. Huh?
my weight can be supported by just 8 eggs. Science! Whoa, careful.
Sonia and I are on a quest to make a maxed out sugar cube bridge. The reason why an arch works is because the weight, or the load, of whatever's on top of the bridge is carried outward along the curve of the arch to the abutments at each end, which carry the load and keep the ends of the bridge from spreading out. No matter what you build your bridge out of, sugar or stone, the science stays the same. Sonia and I are building a much larger bridge out of sugar cubes. We're using glue to help the sugar cubes stay together, just like stone bridges use mortar. And when we're finished, it was pretty impressive.
A massive sugar cube bridge, right? High fives for that.
The moment of truth comes when we take out the support and...
Yeah! It works! Okay. Giant sugar cube bridge, so do you think it'll hold some weight?
I think it definitely should, because right now we have an arch, perfect arch, and the weight is being distributed to the sides, the base,
So that's what it's for, right? We can put weight on there?
we can definitely put some weight.
One to start?
Let's start off with one.
Okay.
And let's see how it goes.
All right.
Here we go. All right.
Yeah, 1 book, yeah! All right, sugar cube bridge,
1 book.
2 books.
Are you nervous?
Yeah! Sugar cube bridge, 3 books.
3 books.
Oh, that was great. It held up 3 books.
3.
Well, technically it held up 2 books and broke on the 3rd.
So it's kind of still far from how much weight we want to hold because we want to cross it.
We definitely want to cross it, so that means we need something bigger and stronger. The cube works.
You're right, because the cubes are great because that keeps the science the same.
Yep.
Right? So something cubular. The milk crate, really?
Definitely, I think we should use those. It's a cube.
It is a cube. A whole bunch of milk crates, and we'll see what we can do.
I think that sounds great.
Awesome. Whoa. This is a Prince Rupert's drop.
It's a piece of glass that has a long snaky tail and a bulb at one end.
So what's so interesting about a glass tadpole? Well, I'll show you. And remember, this is just glass. Oh, Prince Rupert's drops are very strong, almost as strong as steel. It's all in how they're made. Molten glass is dropped into cold water.
What happens is the outer part of the drop cools off first, leaving the inner part still hot. When the inner part eventually cools, it contracts, pulling everything in tighter and tighter, keeping it under a lot of tension. And because it's round, the force you put on it is distributed all the way around, just like the force is distributed on an arched bridge.
Until you get to the tail. Just the tiniest break in the tail, and
it explodes. All that energy is released in a chain reaction. Why it's so strong you can hammer on one end, but explodes when you break the other, puzzled scientists for centuries.
But now we know it's all in how it's made.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next applicant. Okay, don't let them see you. Don't let them see you. Okay, magic smoke. And here we go. Big entrance. Behold, it is I, Overwhelmo. You again. I only have to demonstrate magic 1 time, and you have to let me into the Wizard Academy. And last time does not count. So prepare for your mind to be boggled and your eyes to also be boggled, because I shall do a trick. I will just get to it. Here is a book, behold! And now, feast your stupefaction as I produce another book, ha-ha! And then 2 or 3 more times, behold, that's good. Behold! And now, look upon the wonderment as I stack these books on top of each other, like this. And now, feast more stupefaction as I cleverly move the books off the table. And now, Now comes the magic word. Now, I say the magic word. The magic word! And behold, the book is levitating. It is completely off the table. I have done it. Magic!
No.
No?
Not magic, that's science.
But the book is levitating.
No.
Look at it, it's not even touching the table.
No, it's being supported by the books below because of the center of mass.
Preposterous.
I'm afraid it's very preposterous. Each book is balanced on the one below in a way that the center of mass is behind the edge of the book below. And the entire stack's center of mass is behind the edge of the table. So it may look like magic, but it's science.
So, I can't get into the Wizard Academy?
No, I'm afraid not.
Aye, good. Alakazam! You will rue the day that Overwhelmo did not. I will return, and then you will see. Oh, ow.
Sonia and I made a large bridge out of sugar cubes, and it didn't hold much weight. So now we're going to try making another arch bridge, but instead of sugar cubes, we're going to use milk crates.
There we go. I've made some abutments out of giant crates, and this is where we're gonna start our bridge, and they start there, and it goes in a big arch, but we're gonna be using...
I brought milk crates!
Milk crates! High fives, high fives.
So we start our bridge.
This is a straight line, it's not an arch.
It's not an arch.
But it's clear we have a problem.
Okay, ready?
That didn't work, Phil.
It's like we're back to the beginning again. So this is like two straight lines.
We have two straight lines,
it's
yep.
Like a triangle.
We need an arch, so we're gonna need a support.
Sonia and I build a support to help us make a curve the milk crates can follow. But after we finish stacking, there's a problem.
It doesn't look very solid.
Yeah, it doesn't, does it?
Here.
Oh, yeah. Because there's a gap at the top of all of them. Look, that one, there's a gap. There's a gap there.
There's a big
There's a
one
gap
here.
there.
It's
Well,
not
I mean,
making our bridge very solid.
There's only one way to find out for sure.
You can try it.
Is to pull this out and see if it stands up.
Let's do it.
Okay. So, didn't stay up.
Didn't stay up.
Okay.
That's all right, though.
I'm not sure why it isn't staying up. Like, the sugar cubes were cubes.
That's a cube.
Milk crates are cubes.
But we did change the shape of the cube.
Oh, yeah! If you remember, when I first built my sugar cube bridge, it didn't work with cubes. You have to sand the cubes down to make them into trapezoids. You can't build a perfect arch out of cubes.
So they were wider here and then narrower there so that they had... Oh, so that's the problem.
Yep.
So I could, like, cut it? I could cut it. I could cut it.
You could.
I could cut it.
That's gonna take a long time, though.
If we cut the milk crates into trapezoids, everything will work, right? Right?
We take a milk crate and with the right safety gear, we cut it so we can reshape it into a trapezoid.
Good.
And it works. But
It's gonna take a long time, isn't it?
Definitely. So how about this? I have an idea. So remember when we did the experiment and we had lots of V gaps?
Yeah?
How about we put some wooden wedges into those gaps to make it one secure structure?
So it was sitting like this.
Exactly. So what we're gonna do is insert wooden pieces right here, so we'll fill those gaps.
I get
and
it.
we'll make it one secure structure.
Instead of cutting all of our milk crates, we can keep the milk crates.
Yep.
And they can be solid and we just add to it rather than take away.
Taken away, exactly.
That is a smart idea. Okay, let's make some wedges.
All right.
Oh, hey, how you doing? Let me guess, you want to build a strong structure, something that'll stand the test of time. Well, you know you gotta use the right kind of shapes. Look at this, a square. Now, squares have gotta be strong, right? Well, maybe. Maybe if you press straight down on it, but watch as I push to the side. Oh no! The thing that I have built is now collapsing because squares aren't in fact strong after all. If only I had listened to Sal's sage advice. Yeah, squares aren't gonna cut it. Fortunately, there's a shape that's strong in all kinds of ways. A triangle. Okay, so you heard of triangles before, good for you. But look at this. You can push down from the top and it doesn't move, or you can push from the side and it doesn't move. Triangles are awfully pointy. How do I build with them? Observe! Ha-ha! Triangle here, triangle there, platform on top. And watch. No matter how I try to shift it, it stays solid. And check this out. Triangle here, second triangle there, and a third triangle shape here. That's like 3 triangles for the price of 2, huh? That's a good deal. So there you have it. The triangle, one of the greatest shapes to build with. This is a house of cards, and if you've never built a house of cards, you should definitely try. Try, because it's not easy. What you need to do is you need to make triangles with the cards. If you do it just right, they'll stay up. Then you take another pair of cards, like that. You take another card, and you put it on top. And it stays up.
Keep on building by making triangles and putting another card across the top like a roof.
Then, when you're ready, you can start to make a second layer.
It takes a lot of patience to make a house of cards. But with enough patience and really steady hands, you might be able to finish it.
There we go. Ha-ha, a house of cards. Now, let's max it out. Shh, backing away slowly. Backing away slowly.
To build our maxed out card house, the Science Max build team and I used large pieces of foam insulation, which were super light and easy to work with. Once we set up the first layer, we needed to bring in a scissor lift so we could keep building the next layers. By the time we got to the top, our card house was 10 meters tall.
Yeah, giant house of cards. And now that I've built a giant house of cards, what do I do with it? I knock it down. Science! I'm gonna build it again.
Sonia and I are rebuilding our milk crate bridge. Since cubes don't work if you're trying to make an arch, and changing the shape of each milk crate would take too long, we're using wooden wedges to fill the gaps at the top of the milk crates. Once we get the wedges in, the milk crates have support at their tops, and they make a perfect arch.
Are you ready?
I'm ready.
All we have to do is pull the wooden thing out, and if it holds up on its own, we've done it.
We pull out the support, and
it stands!
It works! The bridge supports itself! Now it's time for the final test.
We try to walk on this bridge.
So we spent some time making sure our bridge was safe. We added a crash mat, and
we built a second arch.
We sure did.
So that it's a little bit wider, and it feels very solid. So the only thing to do now is to test it.
Test it out.
You gonna do it?
I absolutely will.
All right.
Absolutely.
Sonia puts on a helmet and gives it a try. And sure enough, it works.
Yeah! Milk crate bridge! 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 Woo-hoo-hoo-hoo! Science Max experiments at large. Milk crate bridge!
Yay for science!
High five! High five! Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at water. But water is very heavy, but that's okay because we need it to be heavy for this experiment to work. I don't know if I need that much of it though. Maybe I can get, here we go. Yeah, that's probably all I need. Today, we're going to be building a water-powered car.
You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom.
Trim them down, maybe about that much.
Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick one wheel on, put the skewer through the straw, and
do the same thing on the other
3 sides. Then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base. Bring your cap and then go outside.
Here we are outside. Yeah, I know, we're not really outside, but I have a science lab, and you probably don't, so I highly recommend you do this outside.
And don't forget your safety glasses.
Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with one finger so I can get the cap ready, because we don't want it to react until we can get the cap on, and then kink the straw to keep the pressure inside till we're ready to let it go. Then, at the last second, you want to drop that packet in and quickly cap it and kink the straw. And woohoo! Woohoo! There you go, a water-powered car. Now, I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Anthony! Phil, sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science and Max headquarters. I'll show you.
Phil?
Anthony,
Phil?
I'm here.
Whoa. Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
okay.
Today, I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda, and you pressurize this container, and the water shoots out that way. So the car goes this way.
Ah, Newton's third law. Every action has an equal and opposite reaction.
Yeah, you know your stuff. This is why you're here. This is because I could really use your help and advice on how to make this bigger.
Okay, so we're gonna need a bigger tank to pressurize. So this, what about something like this?
So we need something that can hold pressure. Do you think this would work?
I don't know if we'd wanna...
And we'd have to put like pressure fittings on the barrel, like cut a hole and weld them on. I don't know if that's...
Something tells me this wouldn't work, so
okay,
we need,
sure. I got some other stuff over there maybe that we could use.
Check this out. Yeah, I think this would work. This would work a lot better.
Well, this is my stand-up wash tub base.
Your what?
So we'll reuse it. Yeah?
Okay, you know what I'm thinking now, though? I know this... The problem is, I think this is like an oil drum, right?
It is. It's an oil tank from a house.
And these things are not built for pressure.
You can get water tanks that you pressurize.
Like hot water heaters, yeah, you can pressurize. They're built for that stuff. You pressurize them in your basement, and then the water travels up to like
the top
your
floor.
shower or something like that.
So all we need to do is get a pressurized water tank.
Okay.
Put water in it, put pressure in it, and put it on wheels. And then we open the valve and it goes, right?
That sounds amazing. All right, let's get to it, man. Okay.
I got some water tanks over here in this corner of the parking lot.
Seriously?
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. When you're a professional chef like me, you spend lots of time perfecting the perfect recipes. I know my way around a kitchen, and today I'd like to show you one... That's not the fridge. Oh. Today I'd like to show you one of my favorites. Quail truffle gazpacho cakes on a plate of ice. Oh. Beautiful. And here's how to make it. Take some quail, some truffle, and some gazpacho and put it into a cake. Delicious. And here's the interesting part. How to make the plate of ice. Ooh, how did I do it? Well, I tried many different methods, and none were very successful. But now I let science do the work for me.
So here's what I do. You see, I've got my large block of ice, and I've got a fishing line over the top, and on the bottom, I've got 2 heavy weights. Now we wait.
The heavy weights put pressure on the fishing line. This pressure melts the ice where it's pressing down. As the ice melts, the fishing line moves through the block of ice and eventually cuts its way through.
There we are. My hours of waiting have almost paid off. You see, I've got a perfect line through the ice, and I stopped it just before it finished. It's the pressure of the line on the ice that makes it work. The same thing happens when you use ice skates. You see, it's a very thin line, and your body weight presses down on the ice, melts it a bit, and that allows you to glide across the ice. It also allows me to just pop this off. There you are, you see? Perfect plate of ice to put my delicacy on. Let's just try that now. There we
So I've joined Anthony and we're going to max out our water-powered car. Our small design works by creating gas, which creates pressure, which forces the water out of the bottle, creating thrust. Our new plan is to get a water tank, put it on wheels, and put water in it. Then we use an air compressor to pressurize the air inside. When we open the valve, the water is forced out this way, which causes our water car to go that way.
Okay. Haha! So, water car, maxed out version.
Huge.
Water tank.
And filled with lots of water and lots of air. Too. Yeah, pretty good, right?
Whoa.
It's a lot of it. So,
Did it mess up my hair?
no, you look fine. You look great.
Okay, good.
Now, the only thing left is we just gotta open this valve here, right?
Yeah. You want to do the honors?
Yeah, let's do it, okay.
Okay, here we go. 3,
2,
1, go!
We open the valve and our pressurized tank moves forward. The air pressure in the tank forces the water out with enough force to move the tank.
Awesome! That was awesome!
That was a great run, yeah.
That was amazing.
So, pressurized water tank on wheels.
Totally worked.
Totally works.
Total success, yeah.
So, because this is Science Max, the only thing we can do now is make it bigger.
Bigger,
right?
exactly,
Okay.
yeah.
So, problem is,
I don't think we're gonna find a tank bigger than this one.
Yeah.
So.
because then it would be too heavy, right?
Exactly,
A much
way too
bigger.
heavy. Maybe what we can do is just get a lot more water.
Okay.
And then we find a way to pressurize the water.
Oh, so don't pressurize the whole tank, just the stream of water that's going out
As
of the tank.
it comes out, exactly. Something kind of like a fire hose.
A fire hose, right.
So
we take a big container of water.
Right.
And I guess we would need a pump.
Yeah, like a pump would be perfect.
So then we suck the water out of the container, put it through the pump to pressurize it, shoot it out of a fire hose.
And then our car goes flying.
Goes flying.
Okay.
Yeah, let's do it.
Yeah. All right, amazing.
When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out.
The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of?
Power washer pumpkin carving.
The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home.
Yeah, science!
The Wizard Academy. All you have to do is demonstrate true magic, and you'll be granted entry.
Send in the next candidate. Oh, no, not Overwhelmo.
Did someone say Overwhelmo? No, wait, no. Next. Oh, not that. Okay, good. Okay.
Behold, it is I, Overwhelmo! Welcome back, Overwhelmo. If you can truly demonstrate magic, you may join the Wizard Academy.
A glass of water! No, wait, that is not the whole trick. Okay, hold on. Okay, and this, a waterproof playing card. I put the card on the glass and flip it upside down, and then I say the magic word. The magic word. And behold, magic! Yes?
Is that it?
Yes?
Well, it's not magic.
It is defying gravity.
Nope.
The water would fall and the card would fall to the floor.
It's not magic.
This is magic.
No, it's science.
Horse feathers.
Look, the reason the water doesn't come out is the air at the top of the glass keeps it held in by suction. More air would have to get into this glass to decrease the suction, and because the playing card is keeping a seal on the glass, the suction of the air is holding the weight of the water up.
Boulder Dash!
All right, look, let's do a little experiment then, shall we? Let's move the playing card just a little bit from the edge of the glass. You see those bubbles?
Yes.
That's bad news. Science, not magic.
Well, I will return, and then you will see your mind will be melted by the... No, that's not my music. Hold. You will rue the day when... That's not my... Hold. Overwhelmo shall return.
Our maxed out water car worked pretty well. Now it's time for something even more maxed out. We start with a giant tank on wheels, we add a pump to pressurize the water, and a fire hose to shoot it out the back. What's more, this version is big enough for me and Anthony to ride.
Water car!
So amazing! Is the more super improved water car. This tank holds 1,000 liters. And right now it has 720 liters of water.
We have a pump. That's right, our water pump. So the idea is we take the water from this container out through your hose, really pressurized, going really fast that way. Our car goes really fast this way.
All we gotta do is just turn on the pump and we're ready to go.
So we fire up the pump and the water stream comes out really strong. So strong I can barely hold on to it.
Here we go!
But even so, there's a problem.
What's going on back there? I got it! Yeah.
Nothing happened.
No, nothing really. Well, something happened. We got wet, but it didn't really.
It's too heavy.
Too heavy.
So you're on it and I'm on it. That's a lot of weight. We don't ride it. That's something.
Yeah.
Also, this is kind of going crazy.
Yeah, because if nobody's holding it, it's just gonna flap around.
So we'll have a brace here.
Yeah.
Shoots it that way, that's good.
And then we'll need, I feel like we'll need something to kind of propel it. Maybe a better propulsion system. Kind of like one of those steamboats.
So we put a big paddle wheel here.
Exactly.
And we aim it, I guess we aim it down.
At the, yeah, exactly.
Like that.
And then.
At the paddle wheel, and then the paddle wheel spins, and that propels the car.
Exactly.
Right?
Right.
Okay.
Okay, well.
We can do that. Let's do it.
Sounds good,
Put
yeah.
it together. You know what? I have a paddle wheel because I had a failed hydroelectric. This is called flyboarding. Whoa.
Powerful jets of water are being shot out from this board at my feet. Whoa.
The engine on the watercraft behind me creates the water pressure, which travels up the hose and through the jets. The force of the water is strong enough that I can use it to fly around. So what's the difference between this and a water car? Well,
We don't have to take that much water with us because it starts in the lake and ends up in the lake. So the only water I have to carry is in the hose that goes up to the platform. Woo!
flyboarding is lots of fun, but it takes some practice to get it right. Bouncing on jets of water isn't easy, but I got the hang of it.
It's all due to Newton's third law. For every action, there's an equal and opposite reaction. Physics! Woohoo!
Our maxed out water car didn't work so well. The main reason is that much water is heavy, 720 kilograms.
Yeah.
So Anthony and I have a plan. Rather than rely on the force of the water going straight out the hose, we're gonna put a water wheel on the back of the water car. A water wheel works by catching water in the segments of the wheel. The weight of the water on one side of the wheel causes it to start turning. But we're gonna use the weight of the water and the pressure of the water. Hopefully, both combined will be enough force to turn the wheel, which will drive our water car forward. A little construction, and we have it ready to go.
Okay, so here's the latest version of the water car, water wheel! Yeah. All right.
Yeah, there we go.
We try it out, but there's a problem. The trick with the water car is the water itself weighs a lot. Every liter is 1 kilogram, so our 720 liters we start with is way too heavy to get the car moving in the beginning. But as the water gets pumped out, there's a sweet spot where the weight is low enough the water car might move. But then there's only a little water left, so it's a balancing act. We fill it again and see if we can come up with a plan.
Okay, new and improved version, only half full. So the idea this time is because we're starting with it only half full, right?
Yeah.
Then it'll begin to go a little easier because it won't have as much weight as it had the last time we did it. And Phil, yeah?
I can't even move this thing.
What?
I think there's too much fuel. There's too much. Yeah, there's no way we can move this. There's no way this is gonna be able to.
Even half full, you
Even
can't
half full,
move
I
it.
think we need less fuel. We're gonna get down to like maybe like a quarter or something like that.
The thing is, we ran it from the full tank last time, and it never.
Okay.
It never moved at all.
What if we gave it like a push to kind of help it get over that little bump of energy?
Ah, so give it the first push when it's still got a bunch of water in it. We give it a bit of a push, and then maybe it'll go in its own.
Exactly.
Okay.
Wanna
Yeah.
get it down?
Absolutely. Let's do it.
We start the pump and wait for the amount of water to get to just the right spot. Then we give it a push while it's still kind of heavy to start it moving. Sure enough, that push makes all the difference.
Yeah,
The water car is light enough to roll, has some momentum to keep it going, and the force of the water coming out the pump is enough to keep it moving forward on its own.
Still going. Woo-hoo-hoo. All right.
Amazing! Yeah! Look at it, man! This thing worked like a beauty!
It worked all. It went all the way. That way.
Yeah.
Way to go. The water car, finally a success. It was the push.
It was the push. That's all we needed to get it going.
A bit of a push to get it going and a lot less water, and there you go. It totally works. All right, you want to do it again?
Absolutely!
All right, here we go.
Okay.
See you next time on Science Max Experiments at Large.
So much easier to push it without any water inside it.